Well, welcome to the University of Bristol. My name's Tim Gallagher. I'm the Dean of the Faculty of Science at the university, and it's a pleasure for me to welcome you all here this evening to the second annual Colin Pillinger Memorial Talk. Now, this evening there'll be two talks, so we're getting extra value there. I will be handing over to Nick, Colin's son, to do the introductions, but let me just say what a pleasure it is to be here. This is the second of these lectures, and the first was also a well-attended, great lecture. I heard Colin give a talk here some years ago about meteorites. Probably we're trying to work it out maybe 8 odd years ago. But I'm of a certain age, and I grew up with Michael Burke during the Apollo missions and watched deep into the night many of those, and have been fascinated by this ever since. My area of science is organic chemistry, so it's a little bit different, but I think that doesn't diminish the thrill that one gets around exploration, whatever area of science it involves in. So again, welcome. We have some questions, or an opportunity to ask questions of our two speakers at the end of this evening's talks, and I shall look forward to that as well. But I'd now like to hand over to Nick Pillinger to carry out the formal introductions.
Good evening, ladies and gentlemen, and webcast viewers as well. So as you've just heard, my name is Nick Pillinger, and on behalf of the Pillinger family, I would like to also extend our welcome to you this evening to this lecture. After last year's interesting look at the moon and the lunar samples on which Dad started his career, we thought it was only logical to move on to Mars, and in particular Beagle 2, the project for which he is most well known. Of course, we didn't know at the time of planning this meeting that the mission would once again be so topical. Colin always reminded us that Beagle 2 was not a failure, just deferred success. Tonight we'll be hearing more about that success. Firstly, from Professor Mark Sims, the Beagle 2 mission manager, who will tell us about the project and in particular the recent developments. Then secondly, from Dr. Taff Morgan, who will be talking about the expanding list of spin-off applications from the Beagle project. So I'd like to again thank you all for coming, and hopefully we'll see some of you again next year. But now, please let me introduce Professor Mark Sims to start the evening.
Good evening, everybody. Here we go. Right, so I'm going to talk about Beagle 2, both as a mission and some of the latest results we've got on imaging Beagle 2 on the surface of Mars. And then Taff will follow on with a talk about some of the applications of the Beagle 2 technology. So, how did I get into this? Back in 1969, I was a teenager, and my father brought me to the University of Bristol to see the moon rocks. Somewhere in that queue, I was stood, along with several hundred other people, perhaps thousands in the end, to queue up, walk past a small exhibit of the lunar rocks. So, introduction to me. I'm from the University of Leicester. I'm director of the Space Research Centre there. I'm professor of Astrobiology and Space Instrumentation. As I just said, I saw the moon rocks back in 1969. And I can't remember whether it was Colin or one of his colleagues was kind enough to show me around the laboratory in 1969. And I thought, this is fascinating, looking at rocks from another world, in this case our moon. And I always vowed to, if I could, be involved in space research. This was reinforced in 1976, 77 with the landing of the Vikings on Mars. I should say I'm local. I lived in Keynsham till I was 18 and then went to university. And I've been back on occasions ever since. Back in 1997, Colin started to float the idea of Beagle 2 as a mission on ESA's Mars Express mission and called a meeting in the Royal Society in May of that year, where a group of us went along to listen to what we thought was a completely crazy idea. It was crazy, it was great fun, and as we know nowadays, it came excruciatingly close to fully succeeding. So I became, in August that year, project manager for Beagle 2, which I took that role through to 1999, when industry took over the project management, and I became the mission manager for Beagle 2, which meant I was responsible for the flight operations, flying the spacecraft to Mars, operated on the surface with the science being directed by the scientists organised by Colin at the Open University, and also getting the instruments there to the spacecraft. After we lost Beagle 2, we decided to conduct our own post-mortem. There was a full ESA inquiry, which I'll come back to later in the context of what we've learned of Beagle 2 since. But we did our own inquiry. That was sort of the closure at the time for the team, because we had no information on what happened to Beagle 2. So, why Beagle 2? Why then? It was a unique opportunity in 1997. ESA was proposing Mars Express to fly in 2003. The Allen Hills meteorite 84001 had hit the headlines the previous year with putative evidence of life, though nowadays that's quite disputed. And there was a restarting and accelerated Mars exploration program, including Pathfinder and all the NASA missions since. Why bother with Mars? I should explain that the picture behind me, if I can focus this, is actually the best view you'll get of Mars from Earth. It's a bit of a cheat because it's taken with the Hubble Space Telescope, and you see this red world, thin atmosphere, ice caps, etc. Very cold, very inhospitable to life as we know it today. But 4 billion years ago, 3 to 4 billion years ago, it was probably warm and wet. We have definitive evidence of that. Lots of evidence of water on the surface, and a good location for life to start. So that's why people want to go and explore Mars. At the time, Colin's group and other people within the UK were world-leading geochemists. They still are today. And so it was natural that Colin would propose a lander and try and answer the question, is there or was there life on Mars, using the instrumentation and techniques he developed. Also within the UK, we're very well known for our innovative engineering, our innovative instrument design, and so that folded into the mix of Beagle 2. And it was a unique opportunity back in 1997. It was the only European mission going to Mars. It was take that opportunity or not do it. And Colin saw this as an ideal mission to integrate both the academic interest in going to the planet and the industrial capability within the UK. And of course, a high publicity and education value of doing such a mission as Beagle 2. Beagle 2 science was unique. Objectives at the time, detection of past life, extinct life, or extant life, present-day life, by looking for organic compounds in the soil, or regolith as it's technically termed. Analysis of subsurface material and the regime, its geochemistry, etc. And the first attempt at crude radiometric dating by using the decay of potassium to argon in rocks. All of those have only just started to be achieved by Curiosity a long time after Beagle 2. So the science program was looking at the geochemistry, looking at the minerals, how those minerals are put together in terms of what's called a petrology, looking at chemical and physical analysis of the atmosphere, looking at how the landscape has changed, the so-called geomorphology, and measuring dynamic environmental processes on the planet today. And doing some astronomy on the planet as well, looking at the sun, the bright stars in Phobos and Deimos, particularly the latter in actual fact, because that would enable us, if we got a picture of them, to locate our landing site with high accuracy. In terms of the engineering, you've seen the model of Beagle 2 outside. It's roughly 1.8 by 1.6 meters, not that big. Mass of 69 kilos, of which about 8.7 were for the instrumentation, plus some hardware on Mars Express in order to spin it off the platform. Power is very, very low for Beagle 2. It typically was about 10 to 20 watts. You like to think of it in terms of a modern light bulb. That's the total power that Beagle 2 consumed. And it had lithium-ion batteries. You're all familiar with those in your smartphones, tablets, etc. And solar arrays, state-of-the-art solar arrays back in 2003, built of gallium arsenide to get the maximum amount of power. Thermal design on Mars is tricky because the average surface temperature on Mars is minus 40 degrees C, and at night it goes down to well over minus 100, so you've got to have a good thermal design. A lot of the missions use radioisotopes to generate heat. Beagle 2 didn't. It had a very clever design using a solar collector, and it was designed to operate for a nominal 180 days on Mars, or 180 sols as they're called, talking to both NASA missions, Odyssey, and Mars Express. So Beagle 2, as you can see outside, is this pocket watch type design. Had to fold up in order to get all the things we wanted in the volume we were allowed for Beagle 2. It's highly integrated, no redundancy, and it deployed some of its instruments on a small robotic arm. And we'll come back to that when we come to the questions. So I'm not going to go too much through the details of Beagle 2. Some of that's for the people who are interested in the technical detail. But that's a cross-section of Beagle 2 in terms of its base unit. The gas analysis package you'll hear about a bit later, the electronics, etc., and the transmitter, and the arm, and the so-called pore assembly, which was a combination of instruments which we'll talk about in a second. So getting Beagle 2 to the surface of Mars, the so-called 6 to 7 minutes of terror. It's the same for every mission. You have to slow the thing down. First way you do that is use friction in the atmosphere, which heats the heat shield to very high temperatures. You then want to stabilize the probe at supersonic speeds as it goes to subsonic speeds, so it has a small pilot chute and a rear cover, which were then detached, and then the main parachute was deployed. And Beagle 2, for people who watched the animation, as you saw, was cushioned on its impact by a set of airbags which were inflated with actually ammonia gas. On impact on the surface, the main chute would have cut loose. Beagle 2 would have bounced across the surface and then deployed itself. So on landing, it would have looked something like this, large airbags, which were about 1.2 meters across. Beagle 2, remember at this stage, is still folded up, would have been pushed away by their internal gas pressure. Beagle 2 would have fallen to the surface and then deployed itself. So a bit of project history. Conceived, as I said, back in 1997. First sort of official meeting was in May that year. We then wrote a proposal to ESA, which I hand-carried on a plane to ESTEC in Holland, Noordwijk in Holland, and delivered it with a few hours to spare to the deadline. In May that year, European Space Agency came back to us and said, it's far too heavy. You're going to have to redesign it. So I was actually on holiday in Scotland and I had a plaintive phone call from Colin saying, we've got a problem. What are we going to do about it? So when I got back off holiday, we had a meeting and redesigned Beagle 2, which originally had a small rover on board, down to a static lander of 60 kilos. In the end, it ended up being 69. We then, in 1999, was a busy year in terms of the funding. We got industrially based project manager in February. In July, we got some initial instrument funds. And then later in the year, Lord Sainsbury gave us our initial government backing. The ESA Science Programme Committee, which has to approve all missions, approved us in November that year. And then in year 2000, we were vetted by NASA. John Cassani, who was chief engineer, Jet Propulsion Laboratory at that time, came over and did an extensive review on Beagle 2. His conclusion was, what we're doing is nuts, but it seems to work, so keep going. Beagle 2 was built as a spacecraft from summer 2000 to February 2003, October 2002, which you note is very close to the launch, which is in 2003. We started the flight model subsystem integration, and in January 2003, the lid was closed on the lander for the last time on Earth. The pictures, by the way, up to the right are some very pretty pictures from Mars Science Laboratory. So we got Beagle to the launch site by the skin of our teeth. I think we all fully accepted that. And it was launched on a Soyuz Fregat launcher back in 2nd of June 2003. And 19th of December, we said goodbye to it. It was spun off the main spacecraft. I'll show you a picture of that in a minute. And landing was due in the early morning of Christmas Day 2003. And then we never heard from it. We were expecting a transmission via a NASA spacecraft. We expected a transmission to Jodrell Bank. We heard nothing. March 2004, we essentially closed the book on Beagle 2 and did our own post-mortem. In November 2014, we started to see some images of what could be Beagle 2 on the surface of Mars, and I'm not going to spoil the latter part of my talk by talking about that now. The picture to the top right, by the way, is one of the latest pictures by Opportunity on the surface of Mars. It's starting to explore this valley on the side of this crater, and the column in the distance is actually a dust devil on Mars, which is a few hundred meters across. So back to Beagle 2 hardware. This is a picture of the pore assembly. We have 2 stereo cameras, microscope, Cora grinder, X-ray spectrometer, which looked for the elemental composition of the rocks, and a Mossbauer spectrometer, which looked at the iron content. And then bolted along the back of the pore was a so-called mole, which was this self-burying subsurface drill to go collect a sample from deep beneath the surface of Mars. This is a gas analysis package. More of this later in the second talk. This is Beagle 2, just before we close the lid, showing the pore assembly mounted down in the base with all the shiny material is a multi-layer insulation to keep Beagle 2 warm and happy when it was on the surface of Mars. The pore assembly didn't have any. It was actually designed to work at the ambient temperatures on Mars, and that electronics was worked down to minus 110 degrees C. So the lander, just before the lid was closed, solar concentrator over the battery. The gas analysis package is here, and this is a pore with the robot arm folded behind it. So closing up Beagle 2, delicate process, and then with its parachutes and its airbags, everything had to be stuffed literally into the heat shield, front shield here, rear heat shield at the back. So you can see how small Beagle 2 was. Taken to the launch site, which was Baikonur in Russia, and mounted on Mars Express. Mars Express isn't that big, as you can see by the scale of the people, and Beagle 2 is now covered in rather nifty black MLI, as that is a higher performance than the shiny stuff. And 2nd of June 2003, successfully launched and on its way to Mars. And we checked it out a number of times on the way to Mars, including updating the software. As far as we were concerned, Beagle 2 was healthy and ready to land on Mars. At 8:31 on the 19th of December 2003, Beagle 2 was spun up, and it was spun up in order to give it some stability before it hit the atmosphere. Think of a gyroscope. If you have a gyroscope and you try and topple it, it will tend to stay upright. So that's why Beagle 2 was spun up. And this was a picture from a camera that ESA put on the top of Mars Express, showing Beagle 2 disappearing off into the darkness and off towards Mars, ejected at the correct spin rate and at the correct velocity. So where was Beagle 2 aimed at? It was aimed at a place called Acidus Planitia. It's a big old impact site on Mars. When an asteroid hit 4 to 4.5 billion years ago, it was then backfilled with what we think was sedimentary fluvial rocks and also igneous rocks. And this is a close-up of the Acidus basin. And that little area there, which actually isn't that small, it's over 60 kilometers long, is where Beagle 2 was targeted. So what are you looking for if you lose a lander on Mars? You're looking for something extremely small. 1.8 by 1.9 meters if it's fully deployed. And the list there, which I'm not going to go through, which I'll leave you to read while I talk, shows you all the different characteristics of the various components of Beagle 2. All of which, with the exception of the parachute, are very, very small. The airbags would have deflated, and unfortunately the airbags, we should have made them bright green, but they were orange, and that's the same color as Mars. So they would have disappeared, unfortunately. I'd love to see the airbags in some of the images we've got today. So, how do you look for a lost lander? Well, we looked for a lost lander with Mars Express and the cameras going around Mars at the time, but they're relatively poor resolution. They are good resolution in that they're meters or tens of meters, but you're looking for something which is a couple of meters across at most. 2006, Mars Reconnaissance Orbiter got into orbit with its HiRISE imager, which it's in an orbit of about 250 to 300 kilometers above the surface of Mars, and it can resolve its smallest pixel size is about 25 to 30 centimeters, and we gradually got a series of images across the landing ellipse for Beagle 2, which was recalculated in 2006, shown as the blue ellipse-type shape on the left, and the stripes are the images, okay? So you've got 30 centimeter pixels, you've got red, green, blue colors, you've got stereo capabilities with HiRISE. But each of those strips is 6 by 15 kilometers and contains 1 billion pixels. Beagle 2, at its largest extent, is 8 to 10 pixels across. So it really is needle in a haystack time. Various of people, including myself, started looking through the HiRISE images, and you start imagining things. You start to see Beagle 2 on the surface everywhere. The reason, by the way, there are some images off to the right is when Beagle 2 landed, the atmosphere was pretty thin. We wondered whether it had overflown its landing ellipse. In actual fact, we found it where the green cross is, very close to the center, only 5 kilometers away. And so after a while, you get fed up of looking at rocks, which might have been Beagle 2, and gradually people dropped off looking at the images. A few hardy souls kept going, one of which was Michael Kroon, who worked for the European Space Agency during the Mars Express mission, and actually was part of the operations team which delivered Beagle 2. And he noticed by chance that there was an object in 2 overlapping images. You look at those images on the left-hand side, you'll see there's very few which overlap. And he cycled back and forth between 2 images, and he saw an object which stayed there, meaning it wasn't noise in the camera, meaning it was a real object, and it was bright. And he alerted the HiRISE team in Jet Propulsion Laboratory. They alerted us, and as they say, the rest is history. This is a picture of the Beagle 2 landing ellipse. It's 60 kilometers by 10 kilometers. And this is the little area in which we found Beagle 2. And this is some work done by the University of Aberystwyth, which looked at the heights across that area where Beagle 2 landed. You can see the scale, it's only a few meters, and the slopes are a few degrees, basically. So it was a great place to land. And this is, if you like, the discovery image, which we put out as a press release back in January 2015. Beagle 2 came in on this trajectory here, and we see an object here, which was Beagle 2, an object here, which is a parachute, an object here, which is a rear cover, if you can remember the sequence that we saw in the entry, descent, and landing. Currently, we have 8 images, including some in colour, but we're looking for, ideally, all the components of Beagle 2. This is some image processing done by Tim Parker, the Jet Propulsion Laboratory, on the colour image. Colour image is slightly different resolution. It's the way the camera works. You still see the main parachute. You see some peculiar impact here, which we think is a rear cover. You see Beagle 2 up here, but you also see a bright spot just north of Beagle 2. I'll come back to that in a second. This is a close-up of the impact point, we think, of the back cover and the drogue chute. Why is it black? The soil has been turned to black. Because Mars has a very oxidized surface. If you like, Mars is a rusty planet, and any impact disturbs that surface and exposes soil which has not yet been oxidized, which tends to be darker in color. So Tim Parker did the very best he could, combined all the images together, and we got what we called the Mickey Mouse shape. It's the right size for Beagle 2. It's about 2 meters across. It doesn't cast a shadow by the look of it. It's bright. It's flat, shiny surfaces. More about that in a second. And as you can see, the scale bar is 10 meters. Jan Peter Muller, University College London, who's one of UK's top image processing specialists, has a lot of computer techniques for producing so-called super resolution images. He released this data back in April this year, and you see close-ups of the various targets. Parachute actually might look like a parachute now, the pilot chute and the rear cover, and the lander. And what we now know is the front shield, this bright object we saw. And we'll come back to that in a second. So why do we think it's Beagle 2? Is it not just a shiny rock on the surface of Mars? We have a number of discrete elements. Their expected sizes and shapes, and the height. They're not very tall objects. Beagle 2, as you look at that model out there, it's about 80 millimeters deep, some of the sections of it. They're in the right sequence in terms of the relative positions. You would expect the parachute to be first. You would then expect the lander. The heat shield could land by the lander or even longer. That's what we see. And the pilot chute and the rear cover would be off to one side. There are expected separations. They're the right kind of separations we do computer modeling with. They're the expected color. They're in the expected place. And what led to the recent press release, there is a glint. The image changes drastically with the sun angle it's taken at. So before we get on to that, what should we see? Well, we see a lander. We have very good evidence of that being a lander. We see a rear cover and a pilot chute. We have evidence of that. We see the parachute. We don't see the airbags for the reason I've said, though I keep looking at the images and wondering, is that an airbag? Front shield we see, it's a combination separation, so it's definitely Beagle 2. It's even more definitive after recent work. Unfortunately, ExoMars Schiaparelli lander crashed on Mars a few weeks ago. These are the latest images from HiRISE, showing unfortunately the point at which it crashed, the explosion point with unfortunately bits of the lander around, but you see the parachute, and the parachute does look like the Beagle 2 parachute. As far as I'm concerned, is the last piece of the puzzle in terms of definitively knowing whether it's Beagle 2. So what did the data tell us? Remember, you're looking at a blobby shape, okay? The pixel size is 25 centimeters, even with aligning 180 rocks on the surface, which is what Tim Parker did, and matching the images. This is as good as you get, okay? And you can put Beagle 2 on it, and as you see, it's the right size. So you've got the base section, the lid section, and in this case, 2 solar panels. In the announcement we made in January 2015, we said it was at least 2 panels deployed. And that glint effect kept nagging at the back of my mind. Everybody's familiar with it. If you look down your road on a sunny day, the glint of the sun off the windows down the road, they drastically change brightness and your noticeability depending on what the angle is to the sun. So, as of 2016, the image data is consistent with only partial deployment. Base and lids are open, and 1 or more panels, perhaps maximum of 3, were deployed. But the kicker in all this, if the 4th panel didn't deploy, the radio antenna was under that 4th panel. And that was not a design error. It was the only place we could put that radio antenna, given the constraints that we had in terms of mass and volume of the spacecraft. So as I say, this glint effect kept digging away at the back of my mind. And because of a chat with a friend over coffee one night, I got introduced to a team at De Montfort University. They're named there. And the team who's worked with me at Leicester is also named there. And Jim Clement, who was the chief engineer of Beagle 2 up until beginning of 2004. And the idea we had was to build a virtual reality model of Beagle 2. The younger people in the audience will be familiar with that. A simulation of Beagle 2 on the surface of Mars, and model its optical appearance and its reflections as the sun angle changed. And could we reproduce what we're seeing with the high-rise imager? And we've done that by using our human brain and eye, which is very good at pattern matching. It's also very good at false pattern matching as well, as we all know. But we've done some mathematical techniques as well. We've done correlation analysis. We've done a difference between the simulated image and the real images, and we've ratioed the two as well. And all of this is to try and avoid the problem of image processing. Image processing does potentially add false things to an image. Most of the time it doesn't, but we're trying to derive the deployed configuration of Beagle 2. And the result of all this is shown in this overhead here. This is the original high-rise image, very blobby. So there it is. It's raw pixels. You don't see much in terms of the detail of Beagle 2. This is a simulated 3D image of Beagle 2 on the surface. This is a close-up. And as you can see, 2 of the panels are heavily illuminated at this sun angle. 1 isn't. The base is, and the lid is. And you can actually get a reasonable match between the 2. And in actual fact, you know from that you can work out the configuration of Beagle 2 on the surface in terms of north-south orientation. It will never be an exact match because we have no idea where these pixels start with relation to Beagle 2. We tried a whole series of different pixelations, moving the edge of those pixels across, and this was the best match we've got. And that's actually consistent across 3 different sun angles, and it's consistent with either 3 or 4 panel deployment, with 3 panels matching slightly better. It was a 6-month analysis. There is more we can dig out the data. We haven't so far. If 3 panels deployed, then that perhaps answers what happened to Beagle 2. If 4 panels deployed, and the simulation shows it didn't open to 160 degrees like the other panels, it opened to 130, which was nominal for the mission if it saw enough power. The question is, if that 4th panel did open, why couldn't we talk to it? Is it a timing error, software error, flat battery? We probably never know. And this is a simulation of the heat shield, 3 different sun angles, and these are the reproduced pixelated images. Barely see it there. It's quite strong there. Hardly see it at all there. And these are the real images at the bottom, which I think is a good match, and it means the heat shield is led on its side, sat on the surface of Mars. So what does it mean? To sum up, well, Beagle 2 successfully entered the atmosphere. Its entry, descent, and landing, which is the 7 minutes of terror, worked. The lander software started. Deployment probably started, but maybe didn't finish. Reason, have a long list. Done a lot of engineering analysis, Jim Clement has, and even if the fourth panel deployed, there's at least 21 reasons why it may not have worked. So my personal favourite, this is a human being talking rather than a scientist, would be the bad luck scenario. A hard landing because of the thin atmosphere, perhaps distorted the structure, perhaps punctured the airbags, and Beagle 2 didn't fully deploy. So it's on Mars, it's not lost, it's worked, it was intact on the surface. So, success or failure depends on your viewpoint. It depends on your viewpoint in time as well. 2004, the team, which were over 400 people, worked on Beagle 2, were they were pilloried at the time in terms of this was a failure. What have you done? You've wasted all this money, you haven't succeeded. As we know now, it got not as Rob Manning, chief engineer at JPL, says, you got 99% of the way there. You got the difficult bit done. It's a pity the last little bit didn't actually work. So as I count it as a success. UK and ESA landed on Mars in 2003, successfully entered the atmosphere, first controlled landing on another planet, just ahead of Cassini-Huygens. The entry, descent, and landing system was an engineering success. Okay, you might count the fact it didn't fully deploy, if that's the case, as a failure. It was an innovative project. It bound together academics, industry, and the general public. People still remember Beagle 2 today, as evidenced by the fact that you're here tonight. It inspired many people, children, adults, general public, and the scientists. And from the UK point of view, it trained a whole generation of engineers and scientists in terms of planetary science and engineering, which is led indirectly to the ESA Aurora program and the ExoMars program, the Trace Gas Orbiter, which is successfully orbiting Mars, the Schiaparelli lander, which unfortunately didn't succeed, and the ExoMars rover in 2020. The lessons from Beagle 2 are being used in ExoMars and all sorts of other missions. Again, a success. Didn't communicate after landing, didn't provide science from the surface. It may have operated for some time on the surface of Mars. As a scientist and engineer, I would say the probability of it still operating today is extremely low. As a human being, I'd like to think it's still there. So credits and acknowledgements. NASA, of course, Mars Reconnaissance Orbiter. Tim Parker, Jet Propulsion Laboratory. University of Arizona, which are the principal investigators for HiRISE. Aberystwyth University. Jan Peter Muller's group at University College London. Special mention to Jim Clement. De Montfort University enabled the recent analysis to be done. University of Leicester, where I work, and enabled me to take part in Beagle 2 originally. And a special thanks to Michael Kroon, who found Beagle 2 on the surface of Mars. And a very special thanks to Judith and Colin, who made all this possible. Thank you very much.
Well, I'm with you, Mark. I think it was a success, so I'm sure everyone here did as well. And so what I'd like to talk about is the legacy of Beagle 2. Actually, more the legacy of Colin, really. And it's to do with the team that Colin built that worked on Beagle 2 and other space missions, and what we've been doing to try and translate our know-how and our technical knowledge to solve some of the problems back here on Earth. And there's a list of them there, and I'll probably go through them now with you. But I'll start with GAP, the gas analysis package. So this was took about 1/3 of the Beagle 2 lander. It was there to look for the signs of life on Mars. So it was going to sniff the atmosphere and look for methane, which again is a potential indicator of the presence of current life. It was also going to take rock samples, and it was going to burn the rock samples and release carbon dioxide and look at the stable isotope composition of the carbon dioxide. And that would give us a fingerprint to indicate whether or not there had been life present on Mars in the past. So the gas analysis package is a miniaturization of 3 of our laboratory systems. So these are very old pictures now. These are from our old building, in fact. And these are all mass spectrometer-based systems. They're all about the same size as a family car. So we shrunk all that down into the size of Beagle. And I actually joined Colin to work on the system on the top left there, a system called Miranda. It was a system that my colleague Andy Morse had developed, at least he developed the mass spectrometer part for his PhD. So Colin was actually doing space technology transfer in the 1990s. I joined the group in 1993. So even before we had a name for it, Colin was doing it. So that's the kind of person he was. These systems, the one on the bottom is for doing carbon dioxide. Again, as you can see, the systems are pretty huge. The team that Colin built to miniaturize it is shown here. There are 8 of us, as well as Colin. What's amazing is that 7 of us are still at the Open University. Jenny is working now in senior management, but 6 of us are actually still working in space instrumentation and in technology transfer. And again, you'll see a lot of these faces as I go through the talk. Daz, who's the guy on the right-hand side, he's now left us, but he's a CAD engineer, and he now works in the space industry and has been working in satellite manufacture. At the back left is Simeon Barber, and anybody who came to the talk last year would have heard about the idea of going to the moon and looking for volatiles on the moon. Now, Colin kicked off that project with LVRAP, and it's now Simeon who's picked up that mission. And we hope in 2021 to be part of a European Space Agency and Russian Space Agency mission to the moon, to the poles, to actually look for the presence of water and volatiles. With the idea being that if you've got water on Mars, you can start, on the moon, you can start to use that as a resource. Daz was a CAD designer. On his computer, he had a zoom button. Unfortunately, my finger stays the same size. So this is us actually trying to put together the gas analysis package in a clean room. I'm the one impersonating a teapot on the left-hand side there. The guy doing the work is the engineer who's doing the wiring. But you can see those are the kind of conditions we built Beagle under. And this is actually before it went into the sterile facility, the AAF. So this was actually the clean room before the really, really clean room, which Judith, of course, was very prominent in actually getting us built. And it was the biggest, I think the cleanest place in Europe at the time. This is now an animation of how GAP would have worked. Can you press start, please? On Mars. So you might have seen the video at the very beginning. You'd have seen the arm bringing in a sample. So in a minute, you'll see the arm come down. And the idea was we would collect rocks from beneath the surface of the Martian surface to then give us samples of rock that were not oxidized. It would then drop down into a funnel and then into a carousel system with a series of ovens. Each of these ovens was about the size of my little fingernail. They were made from platinum and capable of getting over 1,000 degrees centigrade. As you'll see, the carousel turns round. It then goes to a tapping station, and a ball was driven down into the tapping station, deforms the platinum bucket. You get the electrical connections, and you can heat your sample up. And you can do that in a stepwise manner, and that allows you to fingerprint what's present in the actual sample. So you've turned the rock into a gas, mainly carbon dioxide, and that then goes into a chemistry set, and the actual sample is then processed to clean it up, and then it goes into the mass spectrometer for analysis. So these are the kind of analyses that Colin and Ian Wright and the rest of the group do with meteorite samples back in the laboratory. So we've shrunk the big lab systems, and we do the chemistry on Mars. So once the gas goes into the reactors, it gets cleaned up, and then it goes into the mass spectrometer. in a minute. So when it enters the mass spectrometer, it's ionized. You'll see in a minute, you'll see some flashing. And that basically turns the gas from neutral to ions. You can then accelerate that using voltages, and then it goes through, as you can see there, through the slits. So that allows you to focus the beam, and the beam gets fired around the actual magnet, which is in the shape of a kind of right angle. It's a 6 centimeter radius. And that allows you to separate the different masses present. So in the case of carbon dioxide, we look at mass 44, 45, and 46. And by looking at the ratio of those compounds, you'll see they'll hit a bucket in a minute, and you can actually count those ions. And by counting those ions, you get a ratio. And by looking at that ratio and comparing it to standards, you can then relate that back to things on Earth and whether or not things are biological or inorganic in origin. And again, that mass spectrometer you'll see a bit later on, we're applying it to some samples here on Earth, but it works in pretty much identical to the way that that gap would have worked. Next slide, please. Now, Beagle 2 was not the first space mission that Colin had worked on. Despite what you might have seen on the TV, these are the people behind the Ptolemy instrument on Rosetta. So Colin, Ian Wright with his long hair there, he had short hair in the previous picture, and two colleagues from RAL Space, Ray Turner and Eric Sawyer. And they proposed Ptolemy as an instrument to go to the comet on board the Rosetta mission. I think it was in 1994, 95. It was funded, and in 2001 we developed the Ptolemy instrument, or by 2001 rather. And this is the Ptolemy instrument, so we'd shrunk something the size of a car down to something literally the size of a shoebox. It was a gas chromatograph, isotope ratio mass spectrometer, but basically it was designed to do similar measurements to Beagle, but different. So it was going to measure different chemical species, and those would have answered questions like, did water on Earth come from a comet? And are the building blocks of life, the organic compounds we're all made from, are they present on a comet? On the right-hand side, you can see Ptolemy on board the actual Philae lander. So we were the very, very first thing that went on the lander. We delivered that in September of 2001. We launched in 2004. We chased the comet for 10 years and 4 billion miles until, of course, we landed. We landed in 2014. Unfortunately, Colin didn't get to see this picture. This was an image taken a month before we landed. So this is probably the world's most expensive selfie. 1.4 billion, but it is beautiful, isn't it? It's an absolutely fantastic image taken by a camera on the lander, looking out over the orbiter, looking at the solar panels and obviously the comet in the background. Again, you can see the jets coming out of the neck. This picture also has one of the oldest and one of the youngest things in our solar system in the same picture. So it's a beautiful image. Before we got to the comet, until about August 2014, we were all working on the assumption that the comet would be the shape of a potato. So it was kind of elongated. Once we had the images back, we then realized it was more like the shape of a rubber duck. So we then spent several £100 getting a 3D printed version of the comet made so we could decide where we were going to land. Having spent all that money on this 3D printed version, we decided not to mark it. And so Andy Morse popped down to Morrison's, bought a 69p duck. Simon's son, Matthew, then marked up the landing site. And in fact, the landing site is J, at Gilkia. That's where we actually did end up landing. It's not where we ended up staying, but it's where we first landed. And so we actually took this to the Science Museum for a kind of, a kids event. And the Science Museum got really excited. And this duck is now saved for history or whatever you want to call it. So just by marking it with a felt pen, we've added quite a bit of value to this Morrison's duck. So if anybody wants to have any more signed, well, I'm sure we can get Matthew to mark them up for you. So now we actually did land, of course, and as you saw, we had a very exciting ride. There isn't time to show you the video, but that week of landing was probably the most exciting, tiring, frustrating, but ultimately satisfying week. And we actually managed to take data almost immediately after the first bounce. So whilst everybody was celebrating at Darmstadt, where all the politicians were, those of us in the Lander Centre knew there was a problem immediately. People knew the harpoons hadn't fired. People knew we were spinning. We couldn't be on the surface. But we didn't care because we already had data. So we got data by sniffing the gas that was thrown up. And if you want to know what a comet smells like, under your chair there should be a postcard. So if you want to look underneath your postcard, look for your postcards. Some of you probably have already smelt it already. This was something we did for the One show. My colleague Colin Snodgrass did. And comets do not smell good. In fact, Alex Jones on the One show, she described it as smelling like her granny's toilet cleaner. I warn you that the smell does linger, so I would put it down. Otherwise, when you walk into home tonight, you'll be smelling a toilet cleaner. So the problem with space missions is they're a bit like London buses. We had 3 together. We had Beagle, Rosetta, Cassini-Huygens. We're still waiting for the next one. So we had to look at how we could use the technology we developed. So here you can see the kind of heritage of the kind of stuff I'm about to speak about. So it started with the kind of systems that Ian and Colin and Monica and other people developed at the Open University for analysing meteorites. We then went through, obviously, Rosetta, Beagle 2, of course. And then we had various other funding sources that allowed us to look at a whole range of different applications for mass spectrometry back here on Earth. And the reason we could do that is because we developed this world-leading infrastructure. You know, the labs we have at the OU are fantastic. We're very well equipped. And again, most of that, of course, was down to Colin's funding activities. And as important to that is, as well as having the technology, it's having the multidisciplinary skill sets. So that GAP team you saw there, we had geologists, we had engineers, we had CAD people, we had chemists, physicists. And when you put that kind of disparate kind of skill set together, which is what space missions do, then you have a very, very powerful resource which you can work in partnership with end users to develop a whole range of new capabilities. So this is just a summary of some of the people we've worked with, and there's over £3 million worth of activities there. And in fact, the most recent one, Leonardo and ESA, is the space mission that's going to go to the moon, and that itself is a £3 million project. Oh, sorry. The most applicable technology that we've developed directly for a space mission is this valve. This is a valve that was used to control the gas on Ptolemy, to allow us to control the flow of gas into the mass spectrometer. We then redesigned it, and we've managed to patent the actual design because we made so many changes from what we originally had. And just last year, we've actually signed a manufacturing license agreement with Surrey Satellites. So Surrey are owned by Airbus Defence, and they're the people who put up geostationary satellites. So who knows, in a few years' time, the reason you can watch your Sky TV may be because it's been controlled by one of these valves. It's also been evaluated by NASA, and NASA are looking at it for Resolve, which is the next Mars mission, or one of the future Mars missions. And again, this valve technology could actually go into space again. And again, we will be using it for the moon mission. The biggest impact project we've had is actually developing a system just down the road in Abbey Wood, the Defence Equipment and Support, MOD. They had funding to look at developing the new successor submarine, which is the Trident replacement submarine, which are the submarines that basically keep us safe. We were approached in 2010 to look at whether or not we could develop a new system for them based on Ptolemy. And we did develop a system. It took us less than 9 months. Although we delivered the box to Glasgow, or Faslane, which is in Scotland. The submarine was there, the box was there, but unfortunately the paperwork wasn't. So we had to wait 6 months before we could actually put it on trial. But this system has been on sea trial, and basically it has changed the way that BAE Systems design submarines for the future. So currently there's an air monitoring system on board, which is an American system. There's only one of them. A submarine can't go to sea without that working. And our system is much smaller, it's faster, it's better, it's cheaper, and will save the government and the MOD a lot of money. But more importantly, it allows them to have 3 systems on board. So it makes the environment much safer for our submariners. And again, there's the project team, and again, you'll recognize at least 4 of those people from a previous picture. So we've broken a 30-year American monopoly. Currently, all UK submarines use US capabilities, but that technology is really old now. As I say, it's faster, it's better, it's cheaper, and it'll be a British company that take this forward. I think that they've just announced they're going to call it Dreadnought. It's going to be the first submarines that are designed to have women on board and have facilities for women. It's the first time they've had an educational facility on board a submarine. So the OU already provides online courses for submariners, but now they will actually have the ability to do training. So it's very nice to be part of this, and hopefully, as I say, this technology will last for the next 50 or 60 years. We do develop systems as well for commercial applications. I like to show this one because it's the first time I've ever been called a boffin. So we developed a robotic system that's been used by the world's largest fragrance provider, a company called Geraint, who are based down in Ashford in Kent, and they produce all the kind of smelly stuff that goes into products like toothpaste and washing powders, shampoos, and all the expensive stuff that you buy. So I hate to burst your bubble, but when you buy really expensive perfume, it was probably made in a factory that used to be run by ICI down in Kent. But we've managed to provide a system that allows them for the first time to do quantitative measurements about their perfumes. And so they're very happy, and again, it would be a nice ref story for us. In terms of health, then probably the longest project we're working on is this one. And the answer to the question is, can dogs smell cancer? Is yes, they can. And so can we. So we've copied what dogs do, and we've built we have used a commercial system, £250,000 worth of equipment, and we've worked in partnership with the clinical partners at Amersham Hospital, but also at Cranfield University, the bioinformatics group, to look for patterns of compounds that could be indicative of cancer. And in fact, this work came about because Judy came to me with a BBC News website article where the original work by the dogs was published just after this, and that was back in September 2004. So we've actually developed not only a test for bladder cancer, but also prostate cancer. And that's really important because currently there is no non-invasive diagnostic test for prostate cancer. We rely on something called the PSA test, which is a blood test. The PSA test, there's over 120,000 positive PSA tests in the UK per year. 80,000 of those are wrong. So men are being told they might have cancer, and then they're going through procedures which are very invasive to then be told that they actually didn't have it after all. So we developed a sniffing test. So again, we can sniff comets, Mars, submarines, and now urine. And we're using the pattern profile to actually allow us to actually identify whether or not the patient has old man's prostate or benign prostate hyperplasia or cancer. And we're hopefully, our accuracy is around about 83%. We've done a sample of around about 100 patients. So the next stage really is to take it forward and actually do blind trials and everything else. And we're looking for partners to do that with. A few years ago, I crossed from academia into the dark side of commercial work. And I blame the older gentlemen in the left-hand side there, Ijaz and Phil. They were 2 guys from RAL Space, 2 professors. And in fact, Ijaz had developed the ionization source on Ptolemy, which I never knew until I met him. They approached me about taking the technology and using effectively, they had an idea for a STFC pattern to look at the gases that cause Helicobacter pylori. So both these companies have been sponsored by the European Space Agency at the Business Incubation Centre at Harwell, so funding from the ESA to do technology transfer, and also from Innovate UK through the Harwell Space Launchpad. The second company, I took a phone call at RAL Space from my business partner Jason, who's the guy on the right. He's a pest controller from Manchester, and he said, I think I can smell bedbugs. Can you build me a machine that'll do it, because my knees are going, I'm getting old. I need to build a machine. So we formed the company, and we're currently in negotiations with the world's largest pest control company on how we take this technology forward. So in terms of Helicobacter pylori, why is it important? Well, actually, I realized when I was preparing the slides that when I joined the OU, Colin had a PhD student who just finished working on this. So that was back in 1993. It's only taken me 23 years to catch up. But the idea is Helicobacter pylori is a bacteria that about 1/3 of the world's population have. Up to 40% of the UK population have had H. pylori. And in the developing world, there'd be up to 80% of the world's population are infected, usually because of poor sanitation and transfer of feces or bacteria. And most people get it through when they're kids. Now, the problem with it is the bacteria gets beneath the mucus layer in your stomach, and it causes ulcers. So it's not stress that causes ulcers. It's now been proven that it's bacteria. And up to 95% of duodenal ulcers and up to 75% of gastric ulcers are caused by this bacteria. It's quite easy to treat with antibiotics and protein pump inhibitors, but the actual difficulty is getting the people to the treatment, or actually to the diagnosis. And up to 3% of the world's population, 3% of those infected with Helicobacter pylori can go on and get cancer. So it's an important thing to treat. And just to give you an idea of the numbers, if you just look at India and China alone, and in fact I was at a presentation a couple of weeks ago where they said that the Chinese government might actually start testing all of their population because it's the issues, the cost of not treating it early on are so huge. So you could be looking at over 22 million tests. What are we going to do? Well, we're going to look at carbon isotopes. Exactly what we did on Mars, but this time, instead of it coming from rock samples, it comes from breath. If you give somebody an isotopically labeled urea tablet, the bacteria break down and metabolize the carbon dioxide, and it comes out in the breath. And you can measure that shift. Now, the difficulty is that most systems are like the lab systems you've seen before. They're very expensive, and they're not portable or deployable. So what we've done is take the concept of the gas analysis package on Beagle 2, and we've built our own 6 centimeter radius mass spec, but one that's affordable. And that can be then taken out to places like India and China and used to diagnose people and get them treated. Bedbugs are a massive problem. They're huge in places like New York, although apparently New York's only the 18th most populous part for bedbugs. I think Boston's the biggest one. London has a huge problem, the hotels in particular. So the one piece of advice I can give you, if you ever put your suitcase in a hotel, never put it on your bed. You put it, you know, the ones you get with the metal, with the straps, that's where you put your suitcase, because they can't climb up the metal. That's why they're there. So we basically are looking for the chemicals. So bedbugs communicate through the signature. You can also find bedbugs if you see little spotting of blood around the place, and so we look for that as well. So to put it into context, there are nearly 600,000 rooms, hotel rooms in the UK. A quarter of them are actually in London, and nearly 5 million in the US. But what I didn't realize is that most hotels are just a brand, a bit like McDonald's or KFC. They're franchised. So actually, you have facility management companies actually doing most of that work. One of which we talked to said, well, we let the customers find them for us. So I won't tell you which brand that was, but most of the really big hotels obviously are taking this very seriously, especially now there is some indication that bedbugs might be zoonotic vectors. So in other words, bedbugs might transmit disease. Up until now, it's never been thought that it did, but there's been a study in Penn Medicine which suggests that it can transmit something called Chagas disease, which is a very nasty parasite which can affect your heart. So increasingly, people are becoming more and more proactive about this. So what I've hopefully shown you today is that, you know, space missions mean you've got to make things small, light, low power. You've got to be rugged, shock vibration proof, and be able to survive environmental extremes like on a comet or on Mars. If you're going to build those kind of systems, you've got to build multidisciplinary teams, you've got to build partnerships, and you know, once you do that, you can then start building new solutions and new technologies, and potentially develop systems that give you new opportunities. So Colin is the person who started me and most of us on that journey. Our journey around the solar system will continue, as I say, in the moon in 2021, but also we're looking for challenges back here on Earth. So if you've got any ideas about what I can sniff next, then feel free to tell me. And I'll just leave you with one message, which I think, you know, sums up Colin basically, which was, you know, he had a dream, he put together the team, he had the belief in us, and as Mark has just shown, we probably succeeded. That's it, thank you.
Thanks both very much. That was fantastic. And I think what we've seen is the challenge around science and technology And to think of the mission itself as the end of the story, I think Taff has shown us that it's very much just the beginning of the story. And where the spin-offs from what we do, from the challenges we face and the way that we go about solving those challenges, the spin-offs from this, I think that's where the imagination really does extend. So we have a few minutes for some questions. We have a roving microphone, because if you don't use the microphone, we won't capture it on the streaming. And I'd also ask Mark and Taff to come up here again to use the microphone to answer any questions. So would anybody care to raise a question? And Tom has the microphone down here. Let's do it nice and close.
A question for Mark. I saw that there was the logo of Rothamsted Research on one of the partnerships. Sorry.
That's me.
Sorry.
Yeah.
And I was just wondering what the project you're working with on that one is.
Well, that particular project was to look at something called the blue tongue virus, which is a zoonotic vector that affects sheep in the UK. Well, it's starting to affect sheep in the UK. Because global warming is meaning that the UK is getting warmer, insects that didn't bite in the UK are now moving further and further north. So Rothamsted and Pirbright Institute and also London School of Hygiene, in fact, London School of Hygiene and Tropical Medicine. So James Logan, who was in the video, was also part of that project. And the idea was, could we smell the sheep to then try and work out that they've been infected? So were they producing different volatile compounds?
Any other questions?
A question for Dr. Morgan. In regard to, sorry, I beg your pardon, for Professor Sims.
I was right, you were looking that way.
Getting me PhDs mixed up. In regard to the Schiaparelli probe, I happened to see a picture of it, and it seemed quite similar to the Beagle in terms of that watch case design. That sort of, is that something that's the Beagle 2 has brought to space science in that approach to lander design?
In some aspects, yes. Most landers, you want a compact shape, so they tend to be round in some cases. Schiaparelli was a bit bigger, had more mass, a different landing technique. It used retro rockets and then would have crashed down on the surface. So, yeah, to some extent, Beagle 2 has influenced things, but those influences were there, I think, before Beagle 2 started. Schiaparelli wouldn't have unfolded. It was rely on its batteries and would have worked for a few days. I feel very sad for the team. Put a lot of effort in, like the Beagle 2 team. It's a tragedy for them and a tragedy they didn't get any data.
I guess this is one for Professor Sims. In passing, you mentioned the need to provide biosecurity on probes going to Mars. Could you enlarge on that a bit? Because I know it makes the whole thing much more difficult.
It certainly does. You're not wantonly allowed to contaminate another planet. It goes under the name of planetary protection. It's an old UN treaty which has been there since the late 1950s in actual fact, and you need to sterilise your spacecraft for two reasons. One, not to contaminate your target, but also not to get false positives from life you may have taken to Mars in the first place. In the Viking days, back in the 1970s, 60s, 70s, when valves were used and good technology like that, which unfortunately I'm old enough to remember, you could put your whole spacecraft in an oven and cook it for 5 days and sterilise any life forms on it. Nowadays, with modern technology, you can't do that, so you tend to sterilise the components and then put spacecraft together in an aseptic or sterile facility. And for Beagle 2, a special facility was built at the Open University for putting Beagle 2 together. and you have to actually do microbial monitoring of your staff as well. Unfortunately, some of us have larger microbial loads than others, and some people had to shave their beards off to stop generating microbes which potentially would contaminate Beagle 2. So lots of complications there in terms of sterilising a spacecraft, getting it to launch pad, keeping it sterile, and operating it on Mars.
I was just going to say, I remember seeing Daz's fingerprints and Judy collecting a plate, and it was disgusting.
You take a typical coin out your pocket, there'll be tens of bacteria spores on it before sterilisation, and you have to clean your spacecraft to an alarming degree. Essentially, you have to do a million-fold reduction in the number of bacteria, typically, or more.
Hi, my name is Des Futek. I used to be a physics teacher, and I'm old enough to remember the Viking landings. I was very young at the time. I'm just kind of curious, really, about all these different Mars landings that have happened over the decades. From the kind of the outsider's perspective, it all seems a bit random, but is there a kind of a progression and a kind of or is it, are they all competing with one another? How does it all work? You know, they all seem to be doing similar things and yet different things. Educate us.
I think you've hit it on the head. They are doing similar things, but different things. Certainly, NASA has a program of Mars landers now. It lost interest in Mars after Viking, didn't go back to 1997 in Pathfinder, and that's progressed through everything to Curiosity we see today. Beagle 2 at the time was a once-off opportunity for Europe to get to Mars, to do its own science, use its own instruments. And that's now morphed into the Aurora program and the rover that will go hopefully in 2020, assuming it's funded. There's a meeting going on next week which will decide its funding. It's a bit of competition, it's lots of collaboration as well. Science is international. People don't necessarily do the same thing, they will do slightly different things. They will go to different landing sites. There's lots of places on Mars we'd like to go to. Unfortunately, some of the more interesting ones are the very difficult ones to get to. The surface area of Mars is about the equivalent land area of the Earth. So pick a site on Earth. Where'd you go? Lots of places on Mars to go, lots of places to explore. And all that constant question, was there life there? Or even did life start there and was transferred to Earth? And so we might be the remnants of, as some wag said, Martian pond scum.
So this would be a question for Professor Sims. Was there a specific ESA bid for a lander to go on Mars Express, or did your team just spontaneously come up with a crazy idea and ran to ESA and say, please put this on Mars? Because you made it sound quite improbable, so I'm guessing there was a proposal there already.
There wasn't a proposal in beginning of 1997. There was Colin's idea to put a lander on it. I think it's fair to say ESA thought a lander was a complication too much. Despite some attempted discouragement, we put together a bid which went to ESA in 1998, and Beagle 2 got selected. Everybody realised that putting a lander on Mars was important. It would do unique science. It would complement the observations from Mars Express from orbit. As I say, the rest is history. We got it there and we launched it. But certainly back in 1997, 1996 in actual fact, I think ESA started dreaming of Mars Express. They didn't consider a lander. They thought it was a complication too much.
I have a question for Professor Sims. So since there are so many Mars land rovers already working on Mars, so is it possible that other rovers can rescue Beagle 2 and bring it back to life?
I wish. Unfortunately, they're thousands of kilometres away. So even at top speed, they would take a while to get there. It's probably a great understatement. It would be nice to think you could drive over and push the panel open and Beagle 2 would work. Unfortunately, that won't happen. I suspect maybe one day, 20, 30 years' time, perhaps even longer in the future, maybe somebody will walk up to the side of Beagle 2 and examine Beagle 2. But unfortunately not. It would be great to rescue it, but practicalities of Mars missions means that's impossible.
Oh, thank you. Probably just to have a nice conversation with NASA.
We'll take one more. Down here, Tom.
Hello, this is a question for Professor Sims. Were there any specific advancements in the electronics for Beagle 2?
Yes, you're taxing my memory now. Certainly it was a very low-powered microprocessor. It was state-of-the-art microprocessor. Trying to think what the type was. It's eluded me at the moment, but may come back. It was a very low power system. It was designed to operate on 10 to 20 watts typically, with peak powers from some of the instruments going up to 30 watts. At the time, it was state-of-the-art solar arrays, gallium arsenide arrays, 3-layer arrays, I think, to get the maximum power. You find a lot of this in the Beagle 2 books that Colin published. Software was quite novel, and it was 2 different software systems. One for entry and descent, and then a multitasking system for the surface operations. What we do know from the images of Beagle 2, that switchover happened because the deployment started. We actually reloaded all the software on the way to Mars, something that is not recommended, but because we were pushing the time limit for preparing Beagle 2. As we operated Beagle 2, we found all sorts of software patches. And it got to a ridiculous stage where we decided we'd bite the bullet and reloaded all the software on the way to Mars, something which is not recommended. But it did work, and we did succeed. We know from the commands and telemetry that software was uploaded, and we now know from the images it did work because deployment did start.
Thank you.
Good. Thank you, everybody. It falls to me just to bring things to a close this evening, and I wanted to firstly acknowledge Mark and Taff for the talks that they have given us this evening, and I'm sure you'll join me in doing that. Taff, dogs can smell cancer. They can also smell truffles. So if you ever develop something that will detect truffles, I'll happily help you test that. I'd also like to thank Judith and Colin's family for creating this opportunity for us all, for supporting this, and we will be looking forward to the third Colin Pillinger Memorial Lecture next year. So I'd also like to acknowledge all of the support that we've had from the family in allowing us to do this. And finally, I think, looking back on this, as I said, this was an area that has always interested me and clearly interested a lot of other people. And we heard from Mark how the challenges that the Beagle mission faced. And we talked about success and failure. And I do wonder if success and failure are the right words here at all. I think success is the right word here. And I think going forward, in terms of looking at what other people have done, one of the things I am reminded of here is, I think, a quote from Isaac Newton, which is that if I have seen further, it is by standing on the shoulders of giants. If we don't take challenges and meet challenges head on, we never progress. And progress inevitably comes with challenges and the overcoming of those challenges. And I think we've seen that whole story exemplified here this evening. So again, I think this goes back to one of the giants, and I think that's who we should acknowledge finally this evening, Colin Pillinger. Good. So thank you everybody for coming. Have a safe journey home. Until next year.